Okay, good morning, students. Today we are going to explain some more problems related to addition of matrices and multiplication of matrices. Next problem. Let fx equal to x square minus 5x plus 6. And A is, the matrix A is 2, 0, 1, 2, 1, 3, 1, minus 1, 0, 1, minus 1, 0. Then find f of a. Then find f of a. If fx equal to x square minus 5x plus 6 and the given matrix A is 3 by 3 ordered matrix 2, 0, 1, 2, 1, 3, 1 minus 1, 0. Then find f of a. Here fx equal to x square minus 5x plus 6. Then f of a means replacing x with a, we get a square minus 5a plus 6 into I, plus 6 into I. Because previously I told to you, since it is a matrix, you cannot add a constant to the matrix. For that, I am writing here 6 into I. By writing this, there is no change in the value. So, f of a is given by a square minus 5a plus 6a, the matrix polynomial here. So, to find this, you are in need of a square, that means a into a, the product of a with a itself, and minus 5a. Therefore, let us consider a square. A square, a into a, that is 2, 0, 1, 2, 1, 3, 1 minus 1, 0, multiplied with itself. 0, 2, 0, 1, 2, 1, 3, 1 minus 1, 0. A square is a into a, the integral power of the matrix. Based on the concept of integral powers of matrix, a square is a into a. Now, taking the product of a with a by row and column product, row to column wise product, 2 into 2, 2 into 2, 0 into 2 plus 1 into 1. First row, first column, elements product sum. First row, first column, elements product sum. Similarly, first row, second column product, 2 into 0, 0 plus 0 into 1, plus 1 into minus. Similarly, first row, third column product, 2 into 1, 0 into 3, of course, plus 1 into 0. This is first row, first column product. This is first row, second column product. That is first row, third column product. Similarly, second row and column wise product. 2 into 2 plus 1 into 2 plus 3 into 1. Second row, first column product. 2 into 0 plus 1 into 1 plus 3 into minus 1. Second row, second column product. Second row, third column. 2 into 1 plus 1 into 3 plus 3 into 0. Similarly with third row and first column product, 1 into 2 minus 1 into 2 again plus 0 into 1, and third row second column, 1 into 0 minus 1 into 1 and 0 into minus. Similarly 1 into 1 minus 1 into 3, 0 into 0. So matrix product is considered row to column wise product. So on simplification, therefore a square equal to, on simplification, this is 4, 0 plus 1, 0 plus 0 minus 1 and 2, 0 plus 0. The second row is 4 plus 2, 0. Second row, this is 1, so that this is 3. 4 plus 2 plus 3. Next, 0 plus 1 minus 3. And next one, 2 plus 3, 0 plus 0. This is 2 minus 2, 0. And 0 minus 1, 0. 1 minus 3, 0. That is equal to 5 minus 1, 2. This is 6 plus 3, 9 minus 2 here, 5, 0 minus 1 minus 3. This is our a square. Similarly, find 5a. 5a and 5a, the scalar multiple of 5 into the matrix A. Scalar multiplication of matrix. Concept 1 minus 1, 0. 5a is, you have to multiply each and every element of matrix with this constant. So 10, 0, 5. This is 10, 5, 15. This is 5 minus 5, 0. This is 5a. So f of a equal to a square. That means 5 minus 1, 2. 9 minus 2, 5. 0 minus 1 minus 3. This is a square minus 5a. 5a is 10, 0, 5. 10, 5, 15. 5 minus 5, 0. Minus 5a plus 6 into I. 6 into unity matrix. 6 into unity matrix is 6, 0, 0, 0, 6, 0, 0, 0, 6. This is our f of a. Now on simplification, this is equal to 5 minus 10 plus 6. 5 minus 10 plus 6. This is minus 1 plus minus 0 plus 0. Similarly, 2 plus 5, 2 minus 5. 2 minus 5, this is minus, plus 0. Adding corresponding elements, you get the required f of a. Similarly, 9 minus 10. 9 minus 10 plus 0. Minus 2 minus 5 plus 6. 5 minus 15 plus 0. Next, 0 minus 5 plus 0. Minus 1 plus 5 plus 0. Minus 3 minus 0 minus 6. So, ultimately f of A is, that f of A is given by 1 and minus 1 and minus 3, here is minus 1 and this is minus 1, this is minus 10 and minus 5 and 4, minus 1 plus 5 gives us 4, minus 3 minus 6 minus 9. So, this is our f of A. Once you replaced with x with A, you get the matrix polynomial. Next one. Next one. Next problem. If A equal to 2 minus 3 minus 5 minus 1 4 5 1 minus 3 minus 4, then find A square. Once A is given, you have to find A square. A square is A into A. A into A means you have to take the product of A with A itself. So, that is minus 3 minus 5, minus 1 4 5, 1 minus 3 minus 4. So, taking the product of A into A, now taking the product of A with A, this is row to column product, first row first column product, 2 into 2 4, 2 into 2 4, minus 3 into minus 1 plus 3, minus 5 into 1 minus 5. Similarly, first row second column product, 2 into minus 3 minus 6, minus 3 plus 4 minus 12, minus 5 plus minus 3 plus 15. And first row third column product, minus 10, minus 3 plus 5 is minus 15, minus 5 into minus 4 plus 20. Similarly, second row first column, minus 2 minus 4 plus 5, second row second column, 3 plus 16 minus 15, and second row third column, 5 plus 20 minus 20, third row first column, 2 plus 3 minus 4, third row second column product, minus 3 minus 12 plus 12, third row third column product, minus 5 minus 15, 1 into minus 5, minus 3 plus 1, minus 15, plus 60. This I am taking row to column wise product. So on simplification we get 7 minus 5. 2. This is minus 18 plus 2, minus 3. This is minus 25 plus 20, minus 5. Minus 6 plus 1, minus 1. This is 4. This is 5. This is 1. Here is minus 3. Here is minus 4. 2 minus 3 minus 5. Minus 1, 4, 5. 1 minus 3 minus 4. Here you can observe. The square of the matrix. The square of the matrix A square is A itself. You can observe that relation. A square equal to A itself. Once A square equal to A, and whereas A is a square matrix, then A is called idempotent matrix. That is idempotent. Idempotent matrix. If A is Aij of n by n square matrix such that A square equal to A, then A is called idempotent. Idempotent matrix. This is clearly an idempotent matrix because A square equal to A itself. Example, that is the best example, of course. A is 2 minus 3 minus 5 minus 1 4 5 1 minus 3 minus 4 is idempotent. Once the square of any square matrix is itself, then it is called idempotent. That is one important point. Now, based on this idempotent concept, one important result is that you can take it as a problem. This is also an very important one. If AB equal to A and BA equal to B, then prove that both A comma B are idempotent. This is also one important result. Once AB equal to A, the product of both A and B equal to A and BA equal to B, and the product exists, both AB, BA product exists, and they are of same size. AB equal to A and BA equal to B, then prove that both A and B are idempotent. Idempotent in the sense you have to prove A square equal to A and B square equal to B with the given relations. Now, to prove A and B are idempotent, let us consider the given relations. Given AB equal to A, let it be 1, and BA equal to B. This is. Now, AB equal to A implies AB equal to A. I am taking the first relation. Taking the product with A on both sides. Taking the product with A on both sides. The product is considered, A is considered as post multiplier here. Hence A into A gives us A square. Otherwise you can write it as A into A. I am taking the product on right hand side with A. That implies here AB into A may be written as A into B equal to A square, since matrix product follows associative law. By associative law, product of matrix. By associative law of product of matrices, you can write AB into A as A into BA. Here A into A is A square. That implies A into, but BA equal to B. BA equal to B by 2. I am using BA as B here. AB equal to A square. But what is AB? AB is A itself. So A equal to A square from 1 by 1. So A square equal to A. Hence A is idempotent. Hence A is idempotent. Therefore A is idempotent. Similarly, we have to prove B also idempotent. To prove B as idempotent, again consider BA equal to B, the second relation. Again consider BA equal to B. Multiply both sides with B. That is B into AB equal to B square. Same concept, same analogy. By associative property of the product of matrices, you can write BA into B as B into AB by associative property. Associative property. But AB is from the relation 1, AB is A, given AB is A. So hence B square equal to B square by 1. But BA is B by 2 itself. BA is given B by 2. Therefore, B square equal to B implies B is idempotent. So once AB equal to A and BA equal to AB equal to A and BA equal to B, then you can conclude that both A and B are idempotent. Next problem. Next concept. Next problem. Under what conditions the matrix equation A square minus B square equal to A minus B into A plus B is true. That is our question. Under what conditions the matrix equation A square minus B square equal to A minus B into A plus B? So, A square minus B square equal to A minus B into A plus B. Therefore, A square minus B square equal to, taking the product of these two, A into A square, A into B. Here pre-multiplier is A, post-multiplier is B. You have to maintain the order. So, AB, similarly, minus B into A, minus BA, minus B into plus B, minus B square. You have to maintain the order while taking the product of these two factors. So, A into A square, A into B, AB. Here 3 multiplier is A, post multiplier is B. Similarly, minus B into A. Here pre multiplier is minus B and post multiplier is A, like that. So, you can cancel A square and minus B square on both sides. So that we get AB minus BA is the null matrix. 0 stands for here, O stands for null matrix. AB minus BA is null matrix. Therefore, AB equal to BA. That means A square minus B square equal to A minus B into A plus B. You can factorize A square minus B square as A minus B into A plus B as and when AB equal to BA. That means the product of the given two matrices follows commutative law. That means both A and B are commute. Commute in the sense the product of matrices follows commutative law. So, AB equal to BA, therefore A comma B are commute. Commute with respect to product of matrix, of course. So, this is the condition for A square minus B square may be written as A minus B into A plus B. So, once A, B are commute only, you can write A square minus B square equal to A minus B into A plus B. Similarly, suppose if you consider A plus B whole square. Once you consider A plus B whole square, this is A plus B into A plus B. Now, A square plus AB plus BA plus B square. A plus B whole square equal to A square plus AB plus BA plus B square. Once AB equal to BA only, it can be written as A plus B whole square as A square plus 2AB plus B square. AB equal to BA only, then only you can write A plus B whole square as A square plus 2AB plus B square. Here AB may not equal to BA, may not equal to BA. Hence, A plus B whole square is not equal to A square plus 2AB plus B square. Why A plus B whole square is not equal to A square plus 2AB plus B square means here AB may not be equal to BA. Once it is equal, then it is A square plus 2AB plus B square. But whereas Whereas if AB equal to BA, then A plus B whole square is A square plus 2AB plus B square. Similarly, A minus B whole square and A plus B whole square plus A minus B whole square. You can write the other integral powers of A plus B. Once AB or commute only, you can write A plus B whole square equal to A square plus 2AB plus B square. Commute means if AB equal to BA only, you can write this like this. Otherwise, these two are not equal. Next problem. Next problem. If A comma B are square matrices of order n by n of course, then prove that A and B will commute with respect to multiplication, of course, if and only if A minus lambda I and B minus lambda I commute. For all lambda be a scalar. Lambda be a scalar. Here A, B are square matrices of order n by n. Then prove that A and B will commute. That means AB equal to BA. If and only if A minus lambda I and B minus lambda I are commute, where lambda being a scalar. To show that, consider A minus lambda I into B minus lambda I as B minus lambda I into A minus lambda I. I am taking these two matrices as commute. This is x, suppose this is y. X into y equal to y into x. Now consider that relation. Once these two matrices are commute, I have to show that AB is commute. So taking the product, that implies in of course implies and implied. Taking the product here, AB minus lambda into A into I. A into I. A into I is A itself. Similarly, minus lambda IB. Maintain the order I into B. Plus lambda square I square. That is equal to B into A minus lambda into B into I minus lambda into I into A plus lambda square I square. Now you can cancel the like terms on both sides. Lambda square I square is same to that of lambda square I square. Minus lambda IB minus lambda IB. IB is BI. So you can write like this, minus lambda A minus lambda B equal to BA minus lambda B minus lambda A, because IA equal to A, BI equal to B. Similarly, IB equal to B, AI equal to A. Now you can cancel both sides, lambda A and lambda B. So that implies and implied AB equal to B. That implies and implied AB equal to BA. Both A and B are commute. So therefore, A comma B are commute. For all values of lambda it is valid. Commute. For all lambda. Next one. Next one. If A equal to AB B square minus A square minus AB, then show that A square equal to null matrix. A square equal to null matrix of order 2 by 2. If A is 2 by 2 matrix, then you have to show that the square of that matrix is null matrix. So A is AB B square minus A square minus A. Therefore, A square is A into A, that is AB B square minus A square minus AB into AB B square minus A square minus AB. I will take the product of these two matrices. Multiply these two matrices with row to column product. Row to column product. First row, first column product. AB into AB plus B square into minus A square. First row, first column product. First row, second column product. AB into B square plus B square into minus A. Similarly, second row, first column. Minus A square into AB plus minus AB into minus A square. Second row, first column. Second row, second column product. Minus A square B square plus minus AB minus AB. So taking the product of A to A itself, we get A square B square minus A square B square here. Here AB cube minus AB cube. Here we get minus A cube B minus plus A cube B. Here minus A square B square plus A square B square, which is nothing but A square minus B square, A square minus B square, 0. AB cube minus AB cube, 0. Minus A cube B plus A cube B, 0. This is also minus A square B square plus A square B square, 0. So hence null matrix of order 2. The square of the given matrix is a null matrix. Once the integral power of A is null matrix, the integral power of positive integral power of A is null matrix, and there exists such least positive integer n, then you can say that A is nilpotent. nilpotent matrix of index n. Once if there exists a least positive integer, once there exists a least positive integer n in such a way, a power n is the null matrix. Once A is a square matrix, of course, then A is called nilpotent matrix of index n. So this is clearly the nilpotent matrix of index 2 because A square itself 0. In certain cases it may be A cube 0 and A square may not equal to null matrix. In such case the index of the such nilpotent matrix is 3. So take the definition of this nilpotent matrix. Nilpotent matrix. As if idempotent, this is one more type. If A is a square matrix, and there exists a least positive integer n such that A power n is the null matrix. A power n is the null matrix. Then A is called nilpotent matrix of index n. Index n. So the above example is the nilpotent matrix of index 2. So this is the definition of the nilpotent matrix. If there exists the least positive integer, you have to consider the least positive integer. Moreover, here in this example, you can observe that once A square is the null matrix, then A cube is also null matrix because null matrix into A becomes null matrix, and A power 4 null matrix, A power 5 null matrix. So all the integral powers of A becomes null matrix. Out of these powers, you have to consider the least positive power, positive integral power to A such that A of that power equal to null matrix. That is called index. Of course, here A cube is also null matrix and A power 4 also null matrix, but you cannot take index as 4 here. Out of these powers, you have to consider the least one. That's why I am taking the least positive integer n, such that A power n equal to 0. Then A is said to be nilpotent matrix of index n. The higher powers may be zeros, but you have to consider the least power as index.